Good morning, one and all. Today we are going to discuss the next topic, which is Myhill Nerode theorem for the minimization of finite automata. Myhill Nerode theorem for the minimization of finite deterministic finite state automata. This is for minimizing the number of states of the finite state automata. If you have a finite state automata, you can easily minimize the number of states of the DF, deterministic finite state automata. Here in this theorem, we have three statements. Now we are going to prove that these three statements are equivalent. That means here the first statement is the set L, which is a subset of sigma star. Sigma is the input alphabet, and suppose that we have a binary string, then sigma is 0, 1, and suppose that alphabetic characters, suppose that sigma is alphabetic characters, then small a to z and capital A to z will be the set sigma. Sigma star means you are 0 or more symbol, you are taking 0 or more symbols from that and you are creating a string. And that is the language which is accepted. Language accepted is a subset of sigma star. Sigma star means you are permuting and combining all the possible symbols from sigma star and the language. For example, suppose that the set of input symbols or set of strings, binary strings, which are ending with 0, 1. That means you can create or you can have an infinite number of binary symbol or binary strings. Among that, suppose that your L is defined as the set of strings which is ending with 0, 1. That means that is a subset of that sigma star. That means all the binary string constitute the sigma star. And suppose that your language is defined by the set of strings which is ending with 0, 1. That is a subset of sigma star. Then for accepting this language, there is a deterministic finite state automaton. That is, if you are defining or if you are creating a deterministic finite automata to accept the set of binary strings which is ending with 0, 1, then this language can be accepted by that deterministic finite state automata. That is the first statement. Second statement is L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. What do you mean by an equivalence relation? As you know, an equivalence relation is reflexive, symmetric, and transitive. An equivalence relation is reflexive, symmetric, and transitive. Reflexive in the sense, if you have a relation x is related to itself, x is related to x. If suppose that you have a relation and suppose that an element is related to itself, for example, equal to relation is x equal to x. Okay, less than or equal to x, less than or equal to x. That means those are reflexive relations. Symmetric relation means if x is related to y, implies y related to x. If x is related to y, y is related to x. And transitive relation is x related to y and y related to z implies x is related to z. So these are, if suppose that some relation satisfy all the three three relation, that means all these three properties it is satisfying, then that is called an equivalence relation. That is called an equivalence relation. And L is the union of sum of the equivalence classes of a right invariant equivalence relation of finite index. Then suppose that you have an equivalence class, or if you have an equivalence relation, then you can partition your entire set. Suppose that this is the entire set. Then if you have an equivalence relation, for example, suppose that say x mod 3. Suppose that x is an integer value, and x mod 3 means mod is remainder after division, and x modulo 3 means either it is 0, 1 or 2. And suppose that this is the set of integers. This is the set of integers, and when you are dividing a number by 3, either your remainder is 0 or 1 or 2. That means now you can divide your entire set of integers into three equivalence classes. This is represented by 0, this is represented by 1, and this is represented by 2. That means you have partitioned that set of integers into three classes. 0, 1 and 2. Here x mod 3 was x related to x mod 3, x modulo 3, modulo 3. Suppose that modulo 3, say now 0 modulo 0 is 0. Okay, and that's all about equivalence relation. And now what do you mean by right invariant node? We'll discuss that later. And let the equivalence relation RL be defined by X RLY if for every Z in sigma star XZ is in L exactly when YZ is in L, then RL is of finite index. This is the third statement, and that statement also will discuss in detail. We will discuss later. Now, for proving this, these three are equivalent. Then we are going to prove that our proof is like this. That means initially from 1 you are going to, or from 1 you are reducing 2. Then from 2 you are reducing 3, and from 3 you are reducing 1. That means first of all prove that 1 is equivalent to 2, and then that is equivalent to 3, and 3 is equivalent to 1. This is the way we are going to prove that. This is the way we are going to prove this. Okay. Continuing with, we are going to prove that 1 is equivalent to 2. We are going to prove that 1 is equivalent to 2. That means here, see, we are going to have, suppose that L is accepted by a deterministic finite state automaton or DFSI. Suppose that L is accepted by a deterministic finite state automaton. Okay. Now we are going to have a relation, say Rm. We are going to define a relation X related to Y. Say, suppose that you have, say, Q0, Q1, and this is Q1. Okay. Suppose that B, suppose that A or B. Suppose that this is a language. The language accepted by this is if the given input is having at least one single A, that will be accepted, and if it is not having any A, that means here the input alphabet sigma is the set A, B. That means input is restricted to small a and b, and in that string, see this picture, that means either you can input any number of ones and zeros, any number of a's and b's, but if you are giving a single a, that will switch to q1 and again that will be accepted. That means this is A or B star. That means this is the entire set. Sigma star means a string which is having A and B. Now we can partition that into two. That means here this is accepting all, or this will accept all strings which is having at least a single A. And if your input string is having at least a single A, that will be accepted by this. And if you have only B's, no A's are there in your string, then that is not accepted, and that is represented by this. That means either a string is having at least single A, or it is not having any A's. Okay, that means this is represented by a string which is not having any A in it, and this is represented by the set of strings which is having at least a single A. That means now you have partitioned your entire input string into two. That means you are going to partition. Suppose that n states are there in your relation, or suppose that n states are there in your finite state automaton. You are going to partition your input into n different equivalence classes. Okay, that means each state of that deterministic finite state automaton represent an equivalence class. Okay, if that state, for example, suppose that you have, say, n states represented by q0, q1, q2, etc. up to qn minus 1. q0, q1, q2, etc. up to qn minus 1. These are the states. And how many states are there? N states are there. N states are there. So now you are going to partition this into n different equivalence classes. N equivalence classes. That means at most n equivalence class can be there. That means q0, q1, etc. up to qn minus 1. This is q0, q1, q2, etc. up to, say, this is qi, qn minus 1. That means this is the start state. And from this start state, you have an input alphabet, and on providing or after processing a string, the finite control will be in any one of these states. And suppose that S0 is represented as the equivalence class represented by Q0. S1 is the equivalence class represented by Q1. Say Si is represented by Qi. That means you have n different states Q0 to Qn minus 1, and you can correlate, or each state is represented as an equivalence class, and that equivalence class is represented by S0. This Q1 is represented by S1. That means on providing, say, suppose that you are providing this, say, 0, 0, 1. When your input is 0, 0, 0, 1, suppose that it reaches Qi. On processing 0, 0, 0, 1, suppose that your finite number reaches qi, then this 0, 0, 0, 1 is 0, 0, 1, 0, 0, 0, 1 is a member of the subclass or the equivalence class represented by Si. Suppose that on accepting say 0, 0, 0, suppose that it reaches q1, suppose that it reaches q1, what is the meaning of that? This 0, 0, 0, that input string belongs to the equivalence class S1. That means, suppose that your input is having, suppose your input is a binary string, then for every binary string, you can partition this into, or that belongs to either one of these n different equivalence classes. Okay, if you provide or if you give any input, then that belongs to either S0, S1, etc. up to Sn minus 1. The last one is Sn minus 1. Suppose that in between q0, q1, etc. up to qn minus 1. Suppose that here you have a final state, say this is qf1. Suppose that here you have a final state, and here you have another final state which is represented by qf2. These are final states. This is a final state and this is a final state, and the equivalence class belongs to this class is sf1, and the equivalence class for this is sf2. Suppose that these are the equivalence classes represented by sf1, which belongs to the state, the final state qf1, and sf2 is the equivalence class which belongs to the final state qf2. Then your language, this language will be the union of sf1 and sf2. That means here suppose that qn minus 1 also is a final state. That means wherever there are final states, that equivalence, the members of those equivalence classes has to be added to this L. Has to be added to this L. Okay, and that means the set L is a subset of sigma star is accepted by a deterministic finite state automaton. Now L is the union of means here in this case L is the union of sf1 and sf2. Suppose that here the final states are qf1 and qf2. That means for some inputs, for some strings or some inputs from q0, it is able to reach either qf1 or qf2. For some string, suppose that the control reaches from q0 to qf1 on processing certain input. Suppose the input string is w. On processing that w, after reading the entire string, suppose that the finite control reaches q1, that w belongs to your language. W belongs to that language, and that is represented by the equivalence class sf1. In another case, suppose that you have a state, say w2 is a string, and on processing that string, that means initially the finite control is at state q0, and upon processing this w2, it is able to reach qf2. Then this w2 belongs to this sf2. W2 is a member of this equivalence class. And now you have, suppose that you have two final states, then you have two equivalence classes sf1 and sf2. You have to take the union of those two. That is the meaning of the second one. L is the union of sum of the equivalence classes. Here you have subclasses S0, S1, Si, Sn minus 1, etc. A number of n different states are there, so n different subclasses or equivalence classes are there. Among that, you have to choose some of them. That means those equivalence classes which represent the final state has to be chosen, and that belongs to, that is here L is the union of sum of the equivalence classes of a right invariant equivalence class relation of finite integer. What do you mean by right invariant? What do you mean by right invariant? Right invariant means, Suppose that you have a relation, say x related to x related to x and y. X is related to y. X is related to y, and suppose that this implies x z related to yz. X is related to yz. Then that means this is a right invariant. X is related to yz. Then it is called a right invariant. Now see, we are going to define x related to y if and only if delta of q0 on x equal to delta of q0 on y. Here the definition, if x is related to y, a string x is related to string y, if and only if delta of q0 x is equal to delta of q0 y. That means x is related to y means they belong to the same equivalence class. They belong to the same equivalence class means q0 upon reading x it reaches some state, and q0 accepting y it reaches the same state. That means q0 upon processing x it reaches some state, and q0 upon processing y some other input that also reaches the same state. Delta of q0x means that is some state. That means these x and y, those two belong to the same equivalence class. X and y belongs to the same equivalence class. That's why x is related to y. X is related to y. Okay. Now this is a right invariant if this is right invariant if x is related to xz related to yz. If this one implies xz related to yz, that means we can prove this like this: xz related to yz means delta of q0 upon receiving xz in equal to delta of q0 upon receiving xz. What will happen? Delta of q0 x comma z. See, what is delta of q0 upon receiving xz means delta of q0 upon receiving x. q0 upon receiving x, you have reached some state, and after that from that state you are going to start the journey through z. Okay, that means from q0 you are processing x. That means upon processing the input x, you have reached some state q, and now delta of qz means from that state you are starting and you are processing z. But as per our assumption, x is related to y. X is related to y is our assumption. Then delta of q0 x is delta of q0 y. That means this one implies, that is, this one implies, that means delta of q0 x can be replaced by delta of q0 on y comma z. What is delta of q0 on y comma z? Which is delta of q0 on yz. Hence, we have proved this. That means this is a right invariant means if x is related to y, x is related to, what do you mean by x is related to y? They belong to the same equivalence class. They belong to the same equivalence. X is related to y means x is some string and y is some other string. And if x is related to y, they belong to the same equivalence class. That means same state. Upon processing x, suppose that from q0, after processing x, if it reaches q3, after processing y also it reaches q3. Okay, that is why if and only if delta of q0x equal to delta of q0y. Okay, then that invariant, this is the right invariant means then xz or yz. That means you are after reaching x, after processing x, which it reaches some state, and after processing y, it reaches some state. If it is processing z again, what will happen? It reaches the same state. That is common sense. That's common sense. Now the proof is like this. That means if x is related to yz, then what is delta of x0 from the left? If you are able to reach the right, that is delta of q0 xz is equal to delta of q0 comma yz. That is the thing you have to prove. For that, you are taking delta of q0 xz. What is delta of q0 comma xz? That means xz is a string. Xz is a string. That means x is having 0 or more symbols, and z is having 0 or more symbols. Here, q0 on accepting x. After processing x, it reaches some state. That means delta of q0 x is some state, and from that state it is processing z and reaches some other state. Now we have delta of q0 x is equal to delta of q0 y. Okay, delta of q0 x is equal to delta of q0 y, and that on processing z, we are from this state or from this you can reduce this. Likewise, from this we are reducing this. That means delta of q0 yz. Simply speaking, if you have at this point in time, you should remember one thing. That means till now we have been discussing a number of states are for a deterministic finite automaton, and each state of the finite state automaton represent an equivalence class, and two strings belong to the same equivalence class if after processing each one of them it reaches same state. Okay, and this is called the right invariant. See, now I think we have deduced or the meaning of this and this is same. That means the set L is a subset of sigma star is accepted by a deterministic finite state automaton. That you know already. Now L is the union of sum of the equivalence classes. That also we have proved of a right invariant equivalence relation of finite index. That means finite index means the number of equivalence classes in a relation. That is called index of an equivalence relation. How many equivalence classes are there? Here, for a deterministic finite automaton, as the number of states are finite, then the equivalence classes formed are also finite. Can have at most a number of equivalence classes. For accepting, suppose that you have one accepting state. You have one accepting state, it is having that L is having only a single equivalence class. If it is having two final states, then the L is represented by two equivalence. That means you have to take the union of those two equivalence classes. If you have say 10 final states, then you have to take a merger of, or you have to take the union of those 10 equivalence classes. Okay. Now you have to prove that 2 is equivalent to 3. That means now you have to prove that here the second statement is related to the third statement. That is 2 is equivalent to 3. This is what you are going to do. For that, I am writing E be an equivalence relation defined in this is a right invariant equivalence relation defined into let E be equivalence defined in 2. That means here we have defined an equivalence relation, a right invariant equivalence relation we have defined, and that is having finite index, and that is represented by this is the equivalence relation. This is the equivalence relation defined in. What is the meaning of that? What is the meaning of that? See, now we have to prove that. What you are going to prove? E is a prove that E is a refinement of RL. RL is, what is RL? Here RL. This is an equivalence relation. That means, see the third statement. Let the equivalence relation RL is defined by X related to Y if for every Z in sigma star, for every Z in, or for all Z in sigma star, XZ is in L exactly when YZ is in L. This is what you are going to prove. Okay, this is what we are going to prove. That means let the equivalence relation RL. Here in the second statement, what you have proved? Here, this is the union of a set of equivalence, sum of the equivalence classes. Now, your relationship that if you have a deterministic finite automaton having n states, or you have a finite number of states, that much number of equivalence classes you have, and among that, the equivalence classes represented by the final state has to be added to this L. That is why we have proved 1 and 2 are equivalent. Now you have a set of equivalence classes, and the equivalence relation is defined by E. Now the equivalence relation, which is represented by the right invariant equivalence relation, is represented by E here. Right invariant, as I told you, what is right invariant? XZ related to YZ. That means if X is related to Y, implies XZ related to YZ. If you are adding Z to the right and adding Z to this Y, then both of those returns the same result. If X is related to Y, X is related to YZ, that is right invariant. Now this relation in 2 is represented by E. That is the right invariant equivalence relation. Now, let the equivalence relation RL be defined by XRL. Here, the equivalence relation is defined like this. The equivalence relation RL is defined by, RL be defined by XRL by if and only if for every Z in sigma star, that means you are appending an Z to the right, then XZ is in L exactly when YZ is also in L, then RL is of finite index. Now, what do you mean by prove that E is a refinement of L? Suppose that, what do you mean by a refinement? What do you mean by a refinement? Refinement means, suppose that you have a relation, say R1. Say this is R1 and R2 is, say, this and this. That means in relation R1 you have 5 equivalence classes, 1, 2, 3, 4 and 5. And suppose that in R2 you have only 3 equivalence classes, and suppose that 2 equivalence classes of R1 is fully contained in R2, and these two equivalence classes of R1 is fully contained in this, and this one is fully contained in this. Now the meaning is R2 is having 3 equivalence classes and R1 is having 5 equivalence classes, and R1 is fully contained in R2, then we call it as R1 is a refinement of R2. Then we say that R1 is contained in R2, or R1 is a refinement of R2. R1 is a refinement of R2. Okay. Now suppose that now you have R1 which is having 5 equivalence classes and R2 is having 3 equivalence classes. Now these two equivalence classes can be replaced with this. These two can be replaced with this, and this one you can keep as such. And now we are going to prove that, I think you got the idea of refinement. Now we are going to prove that E is a refinement of RL. That means which one is having highest index? That means E is contained in RL. E is a refinement of RL means E is contained in RL. That means RL is having lesser index. That means number of equivalence classes for RL is lesser compared to this one, E. Okay. Now we have proved that 1 and 2 are equivalent. In 1, as per 1, what we proved is, if you have a set L accepted by a finite automaton, then that is called a regular set, and that language is accepted by a deterministic finite automaton. Simple. Now here in the second statement, as per our question, suppose that you have n states for the deterministic finite automaton, then you have divided your input into a set of equivalence classes, and the equivalence classes which represents the finite states of the finite automaton are taken, and then take the union of those, and you get then you will get a language, and that is the same as this deterministic L, which represents the deterministic finite automaton. And third one is, now let the equivalence relation RL be defined by X, RL, Y. The equivalence relation for the third statement is, equivalence relation RL be defined by X related to Y. That means the equivalence relation is defined like this: some X is related to some Y if and only if for every Z in sigma. Z is another string which is also taken from sigma. X is in L exactly when YZ is in L. Then RL is of finite index. Okay. Then RL is of finite index. The proof is like this. We know that X is related to Y. We know that X is related to Y. X is related to YZ. X is related to YZ for all Z. For all Z, as per our definition of, as this is a right invariant, thus 2, as per 2, this is a right invariant equivalence relation. Right invariant equivalence relation means, if you are appending a string to the right of X and right of Y, if X is related to Y as per our equivalence relation, which is E, X is related to Y, then as this is a right invariant equivalence relation, X is related to YZ for every Z. For every Z, then we can say that X, RL, Y. X is related to Y, where E is of finite index. E is of finite index. X, RL, Y. X is RL, Y, and the index of RL less than or equal to index of E. index of RL less than or equal to index of E. I am going to explain this. This is a bit difficult to understand. So I am moving on to a simple problem or simple exercise for doing this. Then you get a better understanding of this. Okay. See, the a finite automaton is Q0, Q1, and you have Q2 on accepting B, on accepting A, this again accepts B, this again accepts B, on accepting A, this on accepting A. Okay. Now see, I am going to have say S0, S1 and S2. Here we have three equivalence classes. Here we have three equivalence classes represented by this is B. And each what from start state we are going to have say epsilon. On accepting epsilon, it is staying in the same state. So this S0 or the equivalence class represented by S0 is having epsilon as an input string. Then on a single B it is staying here BB, BBB, etc. These are the strings which is represented by S0. That means on reading without an input symbol it is staying in the same state. On accepting a single B, on accepting two B's, on accepting three B's, it is staying in the same state. But what are the strings? We are starting here on a single A. Upon reading a single A, it reaches Q1. Then see on AB, it is staying in the same state. Or you can have A, B, B, A. That means this one represent, see, this one, that means A is coming back to Q1. That means all the strings which happen or upon processing all the inputs of that particular string, if your finite control reaches Q1, then that string belongs to this S1. Upon receiving all these input strings, it is staying in the same state Q0. So we have added all those strings to S0. Here we have added all those to S1, and for S2, see, simplest one is AA. Then A. See, one thing you should remember, that means here this is not having any A's. That means S0 is accepting those strings which doesn't have any A's in it. And S1 is accepting all those inputs having A and B, where the number of A's is odd. Here this is accepting the set of input string in which the number of A's are even. Okay. Now see. Now I am going to check whether these three can be merged. And now we have three equivalence classes S0, S1 and S2. These three are equivalence classes. Here final sets are Q1 and Q2. Final sets are Q1 and Q2. Now whether these two are compatible for merging, that means Q0 on accepting, I am going to have say checking whether S0 and S1 are mergeable. If these two has to be, if we can, that means I am going to check whether this and this are mergeable. That means, as I told you, this S0 and S1 are contained in. If this is a refinement of S0 S1, then you can replace S0 and S1 by S0 S1. Okay. See, upon